Yeah, always the whole time. Yeah. I actually have here in the background. She had recorded it. Oh yeah, it's like yeah.
All right, it looks like it's, now it's starting to uptick again. All right, we'll get started though. All right, so welcome everyone to our DTC seminar. And it's my privilege to introduce Dr. Siwei He. I wrote down a few things. Let me know if I get anything wrong here. All right, so Siwei has a bachelor's and master's in engineering in hydraulic and hydropowered engineering and hydrology and water resource engineering. And he later went on to get his PhD in hydrologic science from the University of Wyoming. And then later had a number of different positions here in Boulder. So a research associate at NOAA GSL, a visiting scientist at NCAR, and a research scientist back at GSL. So very familiar face here in Boulder. And currently, Siwei is a assistant professor at Montana State University in the civil engineering department. And so today, he's going to be presenting some results from his DTC visitor project that is focused on evaluating NOAA MP snow and soil processes over the Montana Mesonet. So take it away, Siwei.
Thank you, Catherine, and thank you, everyone. Yes, it feels so good to back to here, and glad to give this and have the opportunity to to give this presentation. So it's like this work was supposed to finish earlier, but many things happened in between, so it has been delayed. But finally, I think we have some good result, and would like to share with everyone. So the purpose of this work is to investigate the performance of NOAA and then to see further how to improve it. So that means this presentation probably raise more questions than provide answers. And so hope like, we can have more discussion on like, on OMP. And also I would like to really appreciate like, this is a collaborative work, like from many, from quite a, few collaborators. I'm sorry that I haven't got a chance to list their names here because I just finished the slides and a few minutes ago. So I haven't got their like permission to put their name here, and they haven't reviewed the slide yet. But I really appreciate their like support and help. So yeah, so since many of you like here are probably quite familiar with NoIMP, so I would like to start with Montana Mesonet. So Montana Mesonet is a network, observed network that relatively new. So it's part of the U.S. Army Upper Missouri River Basin observed network. So the final purpose is to install like many stations. So each station has around 5 square miles represent area. So it's still like ongoing project. So basically it's measure like soil and the snow information. And that's why like we want to evaluate soil and the snow here. So this map shows the Montana Mesonets and the distribution. So you can see those stations mainly distribute over the middle and the east part of Montana. That's on purposely designed for this thing because like the mountain area, like the west part of Montana is mountain area that already have snow town sites. So the east side and it's like plains and don't so far like we don't have good observations. That's why we want to have observations there. And the slow condition over the mountains and the place are quite different. And here is one example to show you like the snow depths. So you can see like for this, I have the station average over the Snowtown side and the Mesonet side. So we can see the depths, they are quite different. Like those plain areas, we had snow like pretty often, but their depths usually not that as significant as mountain areas. But even though the snow depth is not that significant, but the impact still like it's still like important because like for example the albedo surface albedo change, like this two figure shows like the slow depths versus surface albedo. Slow depths from the Mesonet observation, like I gave 2 individual stations here, and the surface albedo from MODIS data. So we can see like when snow is there, the surface albedo changed quite a bit. So that means even we had pretty like relative shallow snow compared to the mountain areas, but they are still quite important in terms of studying net atmospheric interaction. So that make our work more meaningful. So that's about the background. And so now back to NoIMP. So I'm use NoIMP model in this in this project. So the version that NoIMP version that I'm using, I have been using is UFS branch NoIMP. So that means it's slightly probably different from the NCA official NoIMP branch. Could be some difference. And for the forcing data, I used ERA5 analysis data and did our simulation. And the configuration is the same as GFS. So basically, try to see like the performance of NoIMP in that framework. So that's why like, we try to keep as same as possible as GFS. So here is like a screenshot shows you like the different configurations and like for the surface, soil, like different configurations, and those configurations are quite similar to the default NoIMP configuration, and also with only a few exceptions. Like here, those three are the things that are noticed, different from the NCAR non-MP like branch, like the recommend like or the default non-MP and configuration. Otherwise, they're pretty similar. Those are the models and the data. So and then here is the results, like the slope depths. So they did the simulation or analysis for the slope depths from October 1st to May 31. Basically, that's we assume that's like the mainly the snow period for those place. And I calculated the correlation coefficient and the percent bias. So the percent bias, the correlation coefficient is like we all used a lot. So I didn't list the equation here, but for percent bias, you can say it's basically try to estimate what the percentage compared to the observation, like the bias. So it gives like the percentage, so we can compare across different stations. So yeah, so here from here we can see like first we can see is like correlation coefficient varies. Like we had some stations had pretty good correlation, some stations like not as good as we want. So this is the first thing we can see, and then the second thing we can see like even though the bias also like varies from station to station, but roughly we see like more underestimated than like overestimation from the color it's same. So this the thing we noticed about like the who snow season simulation. So we had some station correlation like coefficient was pretty bad, and some stations correlation were like good. So we want to see why. So like here are three stations that had pretty bad correlation coefficient and the time series. So we can see like we know the poor performance could be from many aspects in terms of mountainous. It can be from the forcing data. It can also be from the observation. Like sometimes even we have observations, but that doesn't mean like they are like good quality, and also can be from the model. So those are the three examples show you the band or poor performance. So we can see like their correlation coefficient were pretty low, and percent bias could be pretty huge. So I didn't spend too much time to figure out, okay, which aspect caused those, poor performance, but rather, focus on those stations with strong performance. Like we had some stations that had very good performance. So those are the examples to show you, like had good performance. So that means like we have some stations that we can use to like really, test our model. Over those Mesonet stations. So, but from the who snow season or who like about half year or like more than half year, it's would be a little bit difficult to see the like performance, like the detailed performance. So I choose like based on event-based analysis. So there was a snowstorm in October. Happened over Montana, like the red box here. So you can see like this is snow dust data shows the snow water equivalent, and Montana was impacted by that snowstorm. So we said, okay, let's use this as one example or event to do some analysis. So here is the correlation coefficient and bias for that specific period only. So we can see for that specific period, the model had pretty good performance. The correlation coefficient was pretty like high. And coefficients were like pretty high, like above 0.7 or so, for almost all the stations. And the bias, so the bias varies, like some stations had positive bias, some stations had a negative bias. Then we checked, okay, so and the station average. So we average all the stations and to check the observed slow depths and simulated slow depths. So those the figure shows the station average. So we can see low MP, had pretty good performance, but it's tend to melt snow faster. Like even for example, we can see like here, for example, where low MP had like snow depth even like higher than the observed. But it melts on like earlier than the observed. So that means like the model tend to melt snow faster than it probably should be. So we want to know like, okay, so this is the station average. And then here, another plot shows you like the individual stations. This is one of the station like had pretty good performance. You can see the correlation coefficient 0.94 and bias was, is negative. For the pretty good performance, and we give you here we plot slow depths, the slow water equivalent and sublimation and melt. So basically, we want to check like different components of the snow process. So and also you noticed that here for the sublimation and melt, I provide the percentage over the snowfall, basically because that I want to see like snow mass balance. Like assume we have a snow event, and then the snow will be disappeared like from sublimation, from melt. So I want to see, okay, how much snow disappeared from sublimation and how much from snowfall. From snow melt. So that's why like I provide the percentage here. So from this here, like the first we can see like the snow depth, like we can see it's very consistent from the station average result. So basically like a little bit faster than it should be. And then for the sublimation, which is the third, some plot here, we can see we have dialogue cycle, the sublimation, and also we had like oscillations here. So this is oscillation is the thing like I didn't expect to see like from the results. And the third thing we can see is snow water equivalent change, primarily drawn by snow melt. So we can see like the snow water equivalent, this curve is snow water equivalent, and its decrease very consistent with snow melt. So that's like a third information. So that means snow sublimation, contributes snow disappear, but not that significant. And then the first point I want to say is like for the snowpack, I couldn't have the snowpack mass balance, but this doesn't mean like the model doesn't hold a snowpack balance. The main reason is that like the model output is a little bit difficult. I haven't really figured out which component is which component. Like so that's why like currently I hope I will figure out later like to have a snow mass balance plot later. So some more examples individual station to show basically the same story as like I showed earlier. So then we want what's cause a faster snow melt like in OMP. So there are many reasons could cause a faster, for example, the forcing data or like the model structure, or like the surface flux. So the thing I checked is snow temperature. So I think because snow to be melt, it has to like temperature close to zero, or it has to be zero to be melt. So that I check, okay, what's the snow temperature? So this is one of the stations that had really good performance. So I plot the temperature. So here, this plot have two layers. Why? Because we know like NoIP has a dynamic snow layers, so it can be up to 3. But when snow is shallow, so it probably have only 2 layers or 1 layer. So it depends on the snow depth. So the layer 2 here is the top layer, and layer 3 is like the second layer. So you can see like the top layer responds like temperature changes more quickly than the bottom. So what we found from this plot is like snow temperature change rapidly and oscillated. So this means like here rapidly and oscillation is like from our common sense is they are not reasonable. Because we shouldn't expect like slow temperature, like it's changed so frequently and so rapidly. But unfortunately, I don't have any like observed data to validate this thing. Like I can feel it's unreasonable, but I can't provide any like observation to show this is unreasonable. But from my sense, that's unreasonable. And we checked more stations. Basically the same story. Like I checked a lot of most, all those stations had good performance. Like I purposely choose those stations with good performance, and they had the same story basically. Slow temperature response changed too rapidly, and oscillation had. So we wonder why could this happen? So we checked more surface properties. Sorry for the busy plot here. Basically, we try to include as much information as possible. So for this plot, let's look at one by one. So first panel is slow temperature that I have showed earlier. And the second panel is top two layers of soil temperature. Basically, we want to see if that's, fluctuation, anyway associated with soil temperature. And the third one is surface fraction. Basically, like I said, okay, what's the slow cover fraction and what's the vegetation cover fraction here, and then like the net radiation, shortwave radiation plot here, and then also plot the surface flux, like sensible latent and ground heat flux here, and then the surface exchange coefficient, because we know like for many cases the surface boundary condition is one reason that cause surface flux unstable. And then I plot wind speed and air temperature. So those are all the information that I showed in the plot. And so the oscillation, for example, we want to see why that happened. So we zoomed in this period that in the red box, the oscillation. So what we found is we saw those oscillations in multiple variables, in the multiple surface variables. We can see this oscillation from temperature, slow temperature. We see these oscillations from radiation, for here we saw these oscillations, and we see from surface flux, ground heat flux most noticeable, and also the latent heat flux we can also see. And also we saw this oscillation in the surface exchange coefficient. So so this makes things complex, and we don't know which one cause the oscillation, if which one happened earlier. And also another thing is wind speed. So why I mentioned wind speed here, because if wind speed is 0, then it's probably the boundary assumption is the reason. But here we can see that our wind speed is not that pretty good wind speed. So and I checked more stations, same story for all the stations, oscillations, and for all many surface variables. And so we know this why this thing is complex, because snow temperature and surface flux they interact mixed together. This is I call it the feedback. So for example, for the surface flux, to calculate ground surface flux, we use snow temperature. And to calculate sensible heat flux, we use snow temperature. And latent heat flux, we also use snow temperature. So sorry. So those green box means snow surface snow temperature, top layer snow top layer temperature. So I'm sorry for inconsistent in the notation basically, because I got those equations from different reference. So they're not consistent, but they are the same variable, basically snow temperature and top layer snow temperature. And also those energy or surface flux impact snow temperature. Here, for example, the boundary condition, when we try to calculate snow temperature, we need boundary condition, and this boundary condition decided by surface flux. So they interact and they compound together. So what makes the thing more complex is numerical scheme also can introduce oscillation, because when we solve the heat transfer equation, it's when you use numerical scheme, and that's may like generate oscillations. Currently, we like I think in OMP we use Craig-Nixon scheme, and that's scheme is usually stable, but it could introduce oscillations. So to figure out what's the reason, like I conduct two additional experiment in addition to the control simulation. So the experiment one, basically I use morning Oberhof similarity theory. I think currently like you know, the NoMP would like for the control run still use this public theory, but it's not different from NoMP default one. I think the current one is more to do some change or like try to make that consistent with the boundary layer, like M1 boundary layer. So it's like it's not different from the normal MP like itself. Surface exchange coefficient, and the second experiment is basically to change the, you know, the numerical scheme from implicit, half explicit to fully implicit numerical scheme. So that's guarantee like a stable solution. So those are the two experiments set up that, you know, are used to figure out like slow temperature oscillation. And here are the results. Like so the top panel is the control, the slow temperature profile temperature from the control simulation, the default configuration. The middle is like the surface. Here I use surface basically like from my experiment setup. Experiment one changes the surface exchange coefficient, and experiment to change the numerical. So I name them surface and numerical. So we don't need to, you know, confuse which one is which one. So for the middle layer is the surface scheme, and the, you know, the third panel is the numerical, like with the result from the, you know, after changing the numerical scheme. So we can see like experiment like surface after we change the surface scheme, surface exchange coefficient scheme, it's reduced the oscillation. Like compared to, for example, compared to the middle panel and top panel, we can see oscillation definitely like decreased a lot. Here even disappear, but it's cool. But we still saw like the rapid change is still there. Like this temperature, for example, those temperature changes very fast. And then we can see like we use implicit scheme, numerical scheme, and then no oscillations at all. And the temperature changed much more smooth. So it's like seems more reasonable. Like it's again, like I don't have like data to validate this, but it seems more reasonable. And then I check other stations, similar story. Like, you know, when we implement a different numerical scheme, and it seems the results most reasonable. So this is a happy story. But then I check the other snow-related variables. Like for example, here I checked snow depths, snow water equivalents, sublimation, and melt, basically the same variable that I showed earlier. So we have only like snow depth measurements. So we compared, we can see with our most reasonable like snow temperature, and we got like the different from observations depths, snow depths are most, you know, different. So this is, you know, not what we want. But that we can see like snow melt was impacted by the, you know, the different experiment. Like when we changed the surface exchange coefficient, like the, you know, snow depths, like control, like the surface different from the control, and when we change numerical scheme also like different. So we can see their impact on the result. So this is like the slow related variable, and basically the same story. So, and we also did a station average, like we average all the snow depths through all the stations, and we can see even more clear, like with this new numerical scheme, our like snow melts and like slower than, you know, the default configurations. So I you know, from the snow depth validation, that's means like even like we got reasonable snow temperature profile, but the results are not as good as default configuration. But for that temperature, slow temperature, are also like pretty concerned about like that rapid change is not reasonable. So, and then I checked the surface like flux from different environments. Here, like just shows you like the sensible heat flux, latent heat flux, ground heat flux, and surface exchange coefficient. So we can see they are like different from different experiments. But again, here I couldn't tell you why like those snow melt because it's like totally coupled system. So it's like change one like impact snow melt rate, and then those surface variables are different. I don't have like a clear like one sentence summary said, okay, that's why we had like snow or snow melt from change numerical scheme. And I did a lot of event-based analysis. This is from January 5th to February 2nd. And, similar story, like just same. I did also like, we had also had oscillations and in the snow temperature. And, but then when we use numerical scheme, we get like smooth, seems reasonable result. But then, we got like snow melt. From like if we compare it to snow depths. So this is what about the snow depths. So yeah, and then like let's jump to the soil moisture. So those are all the like the the investigation or the study on the snow components so far like on this project. And then for the soil moisture, so to validate the soil moisture, it's not an easy work, as usually like the model results are near average, while the observations are always the at a specific location. So here, like I shows you like the observation and the model. You can see each black line represent like near a place that a sensor where the sensor is. So we have the measurement soil temperature and soil moisture measurement at 5, 10, 20, at those depths. And our model default and configuration is 4 layers, and those are the thickness of each layer. So, to make the comparison reasonable, this is what I used in terms of comparison. Basically, I assume the first layer, okay, you measure like the measurement at 5 centimeters, but the thickness is 10 centimeters. So I think, okay, if we assume that soil moisture and temperature is like linear, then the middle should be like the mean average. But again, like this assumption is not necessary validate all the time. It's sometimes like soil condition can be changed quite a bit in 10 centimeters. So, and then model layer like layer 2 versus 20 centimeter measurement, and then model layer 3 versus like, because we have top layer and the bottom, we thought if we average them, then we will get like the mean value. So this is what I did. But again, like for the soil moisture validation, I have less confidence on than like snow depth validation. And so here I compared like the correlation coefficient and percent bias. So like the top panel, like the first row is the first layer, the second row is the second layer, and the third row is third layer. So those are the like the special condition or special distribution of the soil comparison. So again, basically we can see like it's kind of like performance varies from station to station. We had good performance, we had bad performance. And the thing that we can see like, if we think our like comparison like reasonable, then we see like the layer 2 seems like here in terms of correlation, it's tend blue, like has more blue like dots than the rest. So like we think correlation coefficient were higher, And for the third layer of the model, we had more like red dots. That's we assume okay that we can see like the correlation with observation were narrow. So those other thing like other conclusion we can see from the comparison in terms of soil moisture. And if we saw like the percent bias, then we can see like for the first layer, like for the top layer, and like the percent, it's tend to like more like probably overestimated compared because we have more like the brown colors, and then the second layer and the third layer underestimate, like we have more green dots in the second layer and third layer. So these are the thing like about the soil moisture. Again, this is like exactly one season. Like it's from, it's basically what year 2024, start from October 1st to September 30. So this period cover like cold season and warmer season. So we think that should be a fair time period in terms of comparison. So it has like, cold season, so soil is not as active as in the warmer season and then here is the soil temperature. So soil temperature is very good in terms of correlation coefficient. You can see for all three layers, they all had blue dots. That means the correlation with temperature with observation quite good. But again, the percentage bias, we can see tend to tend to overestimated a lot, overestimated compared to observations. So this is the soil temperature. But overall, it seems like the soil temperature is much more, it's easier to simulate compared to soil moisture. And because soil moisture, we can see pretty diverse results, but for the soil temperature, pretty consistent, results. So here is the time series. So what I have shown is the state spatial distribution, and those are the individual stations. Sorry again for this plot, the busy plot. But if we look at from the big, the top panel, the first row is first layer of soil moisture. So we can see the black line is the observation, and blue line is simulated results. So I have in the soil moisture for the top layer, I plot 5 centimeter observation, and I also plot 10 centimeter observations, just to compare with the observations in terms of time series. So we can see our model in the winter time, that's where there's winter time, the performance kind of complex, but in the summertime or the warmer period, usually our model tend to overestimate the soil moisture. So this is consistent with our special statistic percentage bias. So this is the first layer soil moisture, and then the first layer soil temperature. So the blue line is from the observation, and then black and green line is observation again. Black line is 5 centimeter, green is 10 centimeters. So we can see our simulated soil temperature fluctuation, the magnitude in terms varies quite much bigger than the observations. You can see the observed soil temperature fluctuations, the magnitude smaller than the simulated result. So this is the first layer, and then the second layer soil moisture. We can see the second layer soil moisture usually is varies, but not as frequent as first layer. And the observation is 20 centimeter, from 20 centimeter soil moisture observation. So we can see from the 20 centimeter, the soil moisture variation is already kind of seasonal depends. Like it's not like event. It's like we can see like event impact, but not as often as 5 centimeter and 10 centimeter. And here is a second layer temperature. Very good result, right? As in terms of training, match the training very well. And then the third layer soil moisture and the third layer temperature. So we can see like the temperature is still very good, but the soil moisture like similar to the status measurement, like status metrics that we provide earlier. So this is the soil, and here is a zoom in on the first layer of soil moisture and soil temperature after a snow event. So this is October snow event. The top panel, the first row, is snow depths, and then we can see the response in terms of the snow melt in soil moisture. So I feel like from this like result in terms of soil moisture and soil temperature, I feel like topsoil seems like overly sensitive to surface condition, like response very like significant compared to the measurements. Again, like this could be, depends on many factors, like the soil texture, depends on like the uncertainty in terms of the observation. But roughly, I feel like it seems to sensitive to the surface condition or like soil condition. So this is like the validation of the soil moisture and temperature. And then the last piece of work is like the increased soil layer number. So the reason that behind this work is like current NoIMP have 4-layer default configuration, and we wonder, would that be necessary or to increase the number of soil layers? So I made a very quick, very simple configuration, just evenly split each layer into 2 layers, evenly split each default layer into 2 layers. So that means like we have 8 layers totally, like so that as my new configuration, that's basically like just sensitivity analysis. It doesn't I don't have any like support to like how deep, what's the thickness of each layer. So that's what I did. And then to validate the performance is another problem. Like we have observations, and then we want to validate the model performance. So here is what I used for validation. Like for the control run, like the default configuration and the experiment 3 or the 8 layers, they are slightly different in terms of the the number of layers, and which observation to use. But the story is like when we compare, like this is a control layer, the first layer, but for the new configuration, like for my 8 layers configuration, it's the layer 2. So it's compared the average of 5 centimeter and 10 centimeter. In terms of correlation and percent bias, I didn't see any like significant change or bad or improve or make the things bad or improve the performance. So it's like the same for the layer 2, nothing significant noticeable. It's still like depends on like station depends, and then layer 3 also like not significant improvement in terms of like the statistical measurements. So that's giving me like, I think, okay, we can increase the number of soil layers, but then to validate those necessity of increase there, it's not that easy. Like here from the direct comparison, I couldn't show you that okay, we need to improve or increase the soil layer, or we don't. But yeah, soil temperature is always like better, like no matter you increase the layer or not. But then here is one interesting thing, like I want to draw your attention is like if we compare the time series of soil moisture, like this is one individual station. So in this plot, I have control model on control simulation near 1. So that's like 10 centimeter. And I have 8 near 1 and near 2. Those 2 nears sum up is 10 centimeter, but each one is 5 centimeters. And I have observed temperature at 5 centimeter. So the black line in this plot. So again, for the cold season, we couldn't really tell. But for the warmer season here, for example, after May, then we notice that stronger variability in the first layer of the 8th layer versus the first layer of the 4 layer. So for example, if you see the brown line in this plot versus the blue line, so you can see the brown line always has larger magnitude in terms of the variability than the blue line. So that basically means the first layer of 8th layer, fluctuation or variability is larger than the first layer of 4 layers. And if you compare the blue line, which is the second layer of the 8th layer with the blue line, you can see the green line always has less, variability than the blue line. So that means like those represent the same soil, but it provides the flexibility in terms of like the soil moisture variability simulation. Like it gives you the room or give you the potential to make the soil top layer soil more sensitive, but after the top layer it's less sensitive. So this probably like a good solution. And then we checked more. It's basically the same story. So those are the zoomed in. Basically, like the first layer, it's layers scheme, like temperature or the moisture varies more than the first layer, 4 layer, but the second layer varies less, and then the first layer 4 layers. So this is the temperature, and then the moisture, and then temperature similar story. Like here, you can see I give you the observed and the the model result. So the brown line or this orange line is the first layer of the 8th layer. So you can see like the fluctuation much larger than the green line. But sorry, the blue line kind of probably blocked by the orange line. So it's probably like the variation of the control line should be like in between. So this and then green line tend to close to like smaller. So this is like what we found. And similar here is a zoom in plot. You can see like the green line, the variation is smaller than the brown line, and the blue line you can see is in between. Like it's the variation in terms of variation in between, like the top layer of the 8th layer and the second layer of the 8th layer. So and then this impact that we still check. Okay, how does that impact the surface energy or surface flux? So I checked the sensible heat flux, latent heat flux, and ground heat flux. So in this plot, the top panel, top row is rainfall data. Basically, we want to see like what the rainfall when the rainfall happened. So the soil moisture condition will be different. And so what we found is like for experiment 3 is like 8 layers, so higher sensible heat flux during the dry period. So what I mean is so after rainfall, then we have like a drying period, like rainfall happened here, and then after a while, like the soil become drier, and so the control or the default like the sensible heat flux was smaller than like the 8th layer. So the 8th layer is like the surface heat flux is higher. And then the latent heat flux nor latent heat flux during the dry period. So basically here, when the soil is drier, and then, we basically has nice water able to be evaporated. I think that's, the reason, like we have no latent heat flux. Again, like, and also like for the ground heat flux, we had like, greater variability in terms of the ground heat flux, more variability from experiment 3. So again, like here, I don't have like surface flux measurement to validate if this is like necessary or not necessary, if this is a good change or a bad change. So, but we can see like it's more like a sensitivity analysis to show like a similar story for a lot of stations. So this is a lot of station and basically similar story. So that's about, the soil moisture and the number of soil layer impacts on the soil surface conditions. So that brings to the end of like my presentation. So, I feel like so glad and so honored to have this opportunity to finish this DTC like visiting project. Like I mentioned earlier, like this project wouldn't be, possible without many like of you like support, help, or like, provide information. Especially like this, like, cross institution collaboration, it's definitely need much more like effort to make things happen. And I really appreciate that, we make those things happen smoothly. So yeah, and then, thank you everyone, and any questions? Yeah.
Thank you, Siwei. I do have 2 questions. First, for all these simulation, you are like site independent. Each site have a series of rounds. Have you actually spin up your site enough time to make the condition balanced before you?
Yes, this is like very good question. Like, yes, spin up is necessary. So that's why like I mentioned earlier, like for our simulation, it's from 2010 to 2024, but my analysis more focused on like 2023 to 2024. So basically like, more than 10 years spin up, like simulating.
Thank you. That's great. And then for each site, do you have a site-specific soil type and texture kind of the modification to match the exact condition of each mesonet? Because I realized that a lot of the behavior of your simulated variables seems, if you have the right soil texture, in my opinion, a lot of these behavior may change. I'm just curious if that's the case.
Yes, yeah, the behavior would be like, okay, so the answer is I didn't change, like I don't have the soil texture information for each station. Like they are supposed, like for those Mesonet stations, they will provide soil texture information, but currently not available. And so sometimes they will be available probably. But then like, like you're exactly right. The soil texture, when we change the soil texture, the behavior would be like different, but it would be different from this one, but I don't think it would like those, what I have showed would be like still would be there. So it's yes, like, yeah, very good question. Thank you.
Other questions? If you're online, feel free to raise your hand or write your question in the chat as well. Any other questions in the room?
Very nice talk. Thanks, Siwei. So when you first present the multiple panels of the snow depth oscillation, I also noticed there is a strong oscillation in shortwave radiation. So can you briefly comment on the role of radiation, especially shortwave radiation, and also the interaction with the land surface?
Yes. Yes. Very good question. I also like when I saw this plot, and I think, okay, how could that happen? Like here, my explanation is like because this net radiation, it's depends on the shortwave and non-wave. So income shortwave onward shortwave, income non-wave, and onward non-wave radiation. So this non-wave radiation depends on the surface temperature. So that's like because we have oscillation in the snow temperature, that will introduce to the net radiation. That's like my explanation. Hope that makes sense. Thank you.
All right, Mike.
Yeah, Siwei. Thanks. Sorry, I'm getting an echo here a little bit, but we're kind of always in a constant state of model development, right? And so I'm just curious, like, do you have a plan to use this Montana Mesonet data as sort of a evaluation package of some sort that, we could use or collaborate with you to use on future sort of model evaluation that we have internally?
Yeah, so if like I mentioned, this Montana Mesonet network, I think is a very good data source to validate model performance. The only shortcoming I feel like is no surface flux measurement. But otherwise, yeah, because the data set is there, and I would be happy to explore more based on what I have so far. And I feel like yes, if we explore more, and we will see more what we can do. Currently, I mentioned earlier, I'm sorry, this probably raises more questions than provide answers. Basically, I try to understand the behavior of non-MP, and then see what I can do or what we can do to the model.
Mm-hmm.
Thank you. Yeah.
Yeah, and a lot of these obviously are site locations, right? And in the model, we're dealing with grid sizes that are much larger, and maybe starting to incorporate some additional gridded products that might give us some something to also describe something at the larger scale, right? Just thinking about, say, some of your earlier plots where you're looking at snow cover, very ephemeral, right? It's it's there for a few days and it's gone. It's very difficult to evaluate, the model, because the timing of the precipitation has to be correct. There's got to be a lot of things that are sort of lining up correctly, right? And so I did like the analysis that you had of sort of that one event that had the meltdown period, or you could even do the same thing with soil moisture, dry down periods, so that you can kind of capture is the physical processes in the model correct if we line all those things up temporally, right? So we don't have to rely on some of the forcing as much.
Yeah, thank you.
All right, I see a comment from Jeff Beck. Jeff, do you want to speak to your comment, or otherwise I can read it?
I can just mention that Siwei, whatever that numerical option was, I didn't quite follow everything. It looked like it improved not only the oscillations, but the snow melt rate looked much better. It's just that the scheme produced too much snow for that event. So that's kind of a win-win on both the oscillations and the snow melt. We just have to fix how much snow fell.
Sorry, what's the, I'm sorry.
So if you go back to, can you go back to your slide where you showed the different options that you produced to try to fix the oscillations?
Yes. Like this one?
The actual average snowfall amount as a function of time. Yeah.
Snowfall, like this one?
Yeah, that one. So the snow melt rate looks much better with numerical. It's just that there's too much snow being produced.
Yeah, so this, sorry. Yeah, so this is, station average, and numerical scheme changed. I haven't really investigate what like the reason, if that's like from numeric, error, or if that's the real, like, it could be like the real model result, because with oscillation, that's not necessarily like the real model can be it, because it's like introduced oscillation, and so that's the result, not necessarily models. It's like behavior, but then with numerical, it's fixed. The oscillation probably that's the real model behavior, or it's not. So it's, I don't know. Like, yes. So please make comments. Like, thank you.
All right. There's some nice comments from Meg in the chat about CSM. Meg, did you want to speak to that at all?
Sure. I can just add these, kind of weird oscillations you're seeing in different variables here we dealt with in CSM a few years ago too, where it was like, weird oscillations that happen about every other time step between two values. And one of the things we found was that if you increase the coupling frequency between your atmospheric inputs and your land, you can get rid of them. The other option is kind of this numerical solving that you've done here. But if you want to chat more about that, I'm happy to set up a meeting and figure out kind of what's happening.
Thank you.
All right. And then I see Stan Benjamin.
Yeah, you can read it there for yourself, Siwei. But again, I thought that your results with the 8-layer presentation were very reasonable. Go up to slide 79. Let's see if I got the right slide there. Yeah, sure. That's the one I was thinking of. Right. So, we're closer to the observations in the summer period. It doesn't quite dry out as much as the observed, but you get closer to it. And so that was similar to the result that you already knew about, that Tanya Smirnova did, going from 5 layers to 8 layers with the rockland surface model. So you're getting a very nice result here, I think. And I was impressed that you were able to install that and get good results from NOAA MP. So, and then my last question there is, are you publishing this? Are you putting together a manuscript publishing these results?
Oh, thank you so much, Stan. Thank you. I think need to make this publishable. I need to do more work, but finally, definitely we want to make this work publishable if possible. The challenge is on my side, basically like the time commit, and I try to, basically like the main driving force is deadline. I need to have like each deadline push me to, back to this project a little bit. But yes, thank you so much, Stan, for your comments. And I would like to, to discuss more with you, because you have more experience in this aspect, to discuss more with you to how to move to the next step, or how to make this work publishable. Thank you.
All right. I see we're at the top of the hour. There's one last comment from Leisha that the NOAA NCOG community are moving towards a 10-layer configuration, and wondering if there's any plans to rerun the experiments.
We'll have to have a new visitor project, Siwei.
Thank you.
All right. Okay. Well, let's go ahead and thank Siwei for a great presentation.